Finally, we come to the concepts of work and strain energy. These are concepts that you may not have encountered very in great detail in your elasticity courses. So we'll spend some time on these concepts. We have already said that problems in elasticity have uh, admit of a scalar function of strains, which we had called the strain energy density. So it's a function of the strains. If you take derivatives of it with respect to the strain, all the components of strain, you get the stress. So this we have stated is another way of stating the constitutive equation, and for linear elastic materials u is a quadratic function of strain, so that you get a linear stress strain relation as the constitutive equation. And also to get the total strain energy density, you have to integrate so you have to integrate this, take epsilon ij on the other side, so you have to do sigma ij d epsilon ij from 0 to epsilon ij to get u at any strain epsilon ij. Now, the total, this has units of energy per unit volume. So in order to get the total energy, this is the total energy that is stored due to the stresses and strains being developed in the body, in the deforming body, due to the applied forces and displacements. So this is the internal energy, and this internal energy is per unit volume. So to get the total internal energy, you have to integrate it over the volume of the body. So this is the total internal energy of the body. Now the total external energy is the work done. So work done by our body forces, work done by our surface tractions, and work done by the concentrated forces on the boundaries of the body, and this is on the volume of the body. So this is the work that is applied to the body by you, but from outside. Now we define the potential energy of the body as the difference between the internal energy stored and the external work done. Wi minus we is known as the potential energy of the body. It is the internal energy stored minus what is known as the potential of the loads. This is the potential of the loads, and that from subtracted from the internal work gives you the internal energy of the body. And now we come to the very important theorem, which is the theorem of minimum potential energy, the principle of minimum potential energy, which applies to elasticity, elastic bodies in particular. So imagine that we have defined what is known as a kinematically admissible deformation field. So it is a displacement field where all components of displacement are defined at each and every point on the body. And I have put this hat here to just tell you that this displacement is not necessarily the true displacement that the body is facing, but it is just a kinematically admissible displacement field, in the sense that it satisfies all the displacement boundary conditions that are defined on delta VU, and it is also everywhere continuous, so it will give rise to compatible strains, right? And it satisfies the boundary conditions. Apart from that, this is completely arbitrary, so this is not the true field. But from this displacement field, you can find, from this kinematically admissible displacement field, you can find a strain by taking derivatives with respect to ui with respect to I, and ui with respect to j, and uj with respect to I. So you can find the fictitious strains from this fictitious displacement, which satisfies the boundary conditions, displacement boundary conditions, and is continuous. Therefore epsilon ij hat will also be continuous. Now I imagine that the body has undergone this strain, and I calculate my strain energy density based on this fictitious kinematically admissible deformation field, integrate it over the volume to find my internal energy stored. And then this is the potential of the loads, work done by the fictitious displacement on the body forces and on the surface tractions gives me the potential of the loads. Internal energy minus potential of the loads is equal to the potential energy as we have defined, but this potential energy now is for a kinematically admissible fictitious deformation field. And now what the principle of minimum potential energy states is that let us have a bag of this function. Let's suppose we have a bag of these functions ui hat, which are all kinematically admissible. We keep on plugging them into this equation. We keep on plugging them into this u hat and generating this pi. And as we do that, for the correct displacement field, when we have hit upon the correct displacement field from the bag, then this pi would be a minimum. The potential energy will be a minimum for u hat equal to u, where u is the actual displacement field. So this is a very, very powerful theorem, and we will show we will showcase its power quite a bit in our in the days to come. But now I will do a small problem just to show you that this basically allows me to guess a solution, to a particular problem. So let's see. Let us first start with looking at how strain energy, internal energy is calculated. So let us assume that I have this truss, but these truss members are made up of a strange material which obeys a, remember trusses can only bear stresses along their axis. So this stress along the axis, the uniaxial stress in the truss, is dependent on square root of the strain, longitudinal strain when strain is positive, and it is minus of the strain, root over minus of the strain when strain is negative, and the stress is also compressive. So it's a strange kind of stress strain relation that we have for this, and we need to find out the total strain energy stored. To do that, we take this hinge out and draw its free body diagram. So we can easily solve this. P is a known force, so F1 turns out to be minus root 3p. So F1 is actually this way. F2 is the correct direction. So if F1 is this way, then this first bar is under compression because it has to be subjected to F1 like this, and therefore F1 from the other side. The other bar is subjected to tension because this is F2 like this and F2 like this. So this is bar 2, which is in tension, and the stress in it is 2p by A2. 2p is the force and A2 is the area. The stress on it is compressive minus root 3p. So once it is a compressive stress, then to get the strains, first I have to use this relation uh, for for this strain. I've done that, and strain will be proportional to square of the stresses. I have to use the upper relation for this, and I've done that, and I've got the strain. Now I have to find the internal energy, and to find the internal energy I will have to integrate u from I'll have to integrate sigma ij epsilon ij. Remember, I'll have to do this. I'll have to do this to get the u. However, I here there's only one component of stress, that is sigma, one component of strain, that is epsilon, and I'll have to integrate it from 0 to epsilon in order to get the u. And I'll do this separately for the two cases. So for the first beam, which is under compression, I'll use the compressive stress, and for the second beam I'll use the tensile stress. Both these integrals can be easily carried out, and this is the result of the integration as per the strains that we have found. And to get the total internal energy, we now have to integrate u over the volume, and the volume are the volumes of the two bars, which is simply A1 L1 and A2 L2, which means that the internal energy stored, just a bit of simplification, is this. So this is how we have to find out the internal energy. We have to get to the stress state at each and every point in the material, integrate over the volume of the body, and that will lead us to the internal energy. Now let us see how this minimum potential energy principle works. Here I have a cylinder sitting on a rigid floor. So this is the floor and subjected to pressure from the top. The axis is x3 this way, and the length, let's say, is L. Now, uh, I assume that so it's told to me that this is a frictionless floor. So on this floor, it cannot move. The surface cannot move in the vertical direction, of course, because of the floor, but it can slip in the x1 and x2 directions because this is frictionless. So uh, this is a guess kinematically admissible displacement field. It is kinematically admissible because u3 is equal to 0 at x3 equal to 0. So on this entire surface, x3 is equal to 0, and therefore on this entire surface u3 is also equal to 0, which satisfies the essential boundary conditions, and therefore this deformation field, we still don't know whether it is right or wrong, but it is definitely kinematically admissible. Now, we now reduce this problem to the problem of finding lambda 1, lambda 2, lambda 3. If we are lucky and this is indeed the correct form of the displacement field, then lambda 1, lambda 2, lambda 3 would give me the three constants, would give me the entire displacement field. So now, based on this, I calculate the strain field. So the strain field is just lambda 1, epsilon 2 to lambda 2, and epsilon 3 to lambda 3. And then, assuming isotropic elasticity, we find out the strain energy density. The strain energy density for isotropic elasticity can also be found as half sigma ij epsilon ij. So this is a form of strain energy density that we are going to often use, and I've used that to calculate this. Please verify this equation. Please verify this equation. Using your constitutive equations, you have only three components of normal stress, and therefore this should be your strain energy density based on this formula. In this formula, remember that ij is a repeated index, so you have a summation over it. Now, this is your U, and on the sides, you have traction free. So these sides are traction free. These walls are traction free, and then on the bottom face, T1 and T2 are 0 because it's frictionless, and on the top T3 is equal to minus P, and based on this you can find the potential of the load. The only traction that will lead to a potential uh, is T3 bar, which is acting on the top and is equal to minus P. uh, it's equal to minus P again because the normal here is 0, 0, 1, and the traction is 0, 0, minus P. So uh, the traction is T3 bar equal to minus P. T1 and T2 are 0. On the lower surface, T1 and T2 are 0 because it's frictionless. So the work done by this is, remember, the work done by the surface tractions is on del V T T dot U ds, T bar dot U ds. So in this case, we have on the top surface, which has an area of A, we have T bar is equal to minus P E3 uh, dotted with U, and that will give you dotted with U, which is lambda 1 L plus lambda 1 L E1, lambda 2 L E2 plus lambda 3 L E3 ds. So now if you take the dot product, this will become over A minus P lambda 3 L D. I've called it dA, so I'll put dA here, dA. This is minus, you have to subtract the potential of the loads from the strain energy. This is the strain energy, so you get a plus sign here, and now you can carry out this integration, and if you carry out this integration, this is the total potential energy that you get. The first term is the strain energy, this is the potential of the loads. Now, now this is a function of lambda 1, lambda 2, lambda 3, we know everything else. So now I'll do del pi del lambda I equal to 0 for I equal to 1 to 3. I'll get three equations. I can solve those three equations for lambda 1, lambda 2, lambda 3, and that is what I'll do. I get these three equations, and the solution to this, it's a tedious but doable process. Solution is lambda 1, lambda 2 is equal to mu P by E, lambda 3 is equal to P by E. So remember this cylinder was subjected to pressure from the top. So lambda 3, so the displacement in 3 direction comes out to be P by E x3, U3 comes out to be P by 3x3, and U1 and U2 are equal and are equal to nu P by E. So this shows that this cylinder, when you press it from the top, it sort of gets shorter, and at the same time it expands in the x1 x2 direction. Okay, so what this problem shows is that we can start from the principle of minimum potential energy and guess a solution. In this case we guess this, and then the number of variables that we need to solve for is dependent on how good our guess is. In this case, I have to determine just three numbers in order to get the solution. And even if I am way off from the true solution, it will still be forgiving and give me an answer to the kinematically admissible displacement field that I have proposed. Okay, so we will expand on this. We will see how this minimization can be done formally, and most importantly how it can be done within the finite element method. Okay, that's in the next video.